Hello and welcome to today's Microchip live stream. We will be spending the next 40 to 50 minutes covering zero drift amplifiers. My name is Kevin Schroeder. I'm a product marketer with the Amplifier team. I'm happy to be joined today by Stefan Bayer, our applications engineer who covers a variety of product lines, including our zero drift amplifiers.
That's correct. Thanks, Kevin, for having me here.
And also joining us today in the booth are two of my fellow product marketers. We have Mitch Polonsky and Rachel Wetton, who will be monitoring the live stream. Welcome.
Hi, yes, welcome. Thank you, Kevin. So my name is Rachel Wetton, and this is Mitch Polonsky.
Yeah, I'm also a product marketer. Careful, I haven't had my coffee yet, but.
All right, so the way that things are going to happen today for this live stream is that Kevin and Stefan want you guys to participate, and there are a couple ways for you to participate. And one of the ways is you can directly chat in the comments below with comments or questions, relative to the topic that we have here. And the second way is that you can send an email, and that email you can be sent at livestream@microchip.com. Okay, so those are just a couple of ways that we want you to be able to participate. We're excited. This is great information about zero drift operational amplifiers. So
easy. Sounds good.
Right. All right. Do you have anything to add?
No, I think we should take it back to Kevin and Stefan.
All right, back to you, Kevin.
All right, thank you, Rachel and Mitch. Appreciate your help. So as I mentioned, today's topic is zero drift amplifiers. We really want to focus, though, on the system level implications of trying to implement this new type of architecture. But Stefan, before we get into that, let's just start with the term, zero drift amplifiers. My understanding is that's an industry standard term.
Yes, I would say it's fair to say that zero drift has become a common term for describing a certain class of amplifiers. That class, or many in the audience may be familiar with that term, or it also stands for other terms that people are familiar with. For example, auto zero or chopper stabilized architectures. Now, it all describes a class of amplifiers that continuously correct themselves and correct their own offset, and also as a side effect, and we will talk about it later, I believe, they shape the noise. So it is a class of amplifier that has a bit more in them internally as your standard linear amplifier.
Mm-hmm. Great. So the self-correcting architecture, obviously a lot different than what you would see in, say, a traditional operational amplifier, which leads to some very specific design considerations that need to be taken into account. Before we get there, though, I believe it's pertinent that we have a high-level understanding of what's going on inside the amplifier itself. In terms of the architecture, I believe that will help to explain how it affects the system-level design. So let's start there. You mentioned there's several different architectures that fall under the umbrella of, say, a zero-drift amplifier. Let's start with, say, a chopper-stabilized, though.
Yes, the chopper stabilized amplifier has become sort of the most commonly used architecture. And to walk you through what's actually in there and describe it a little bit, we've prepared a slide that we wanted to show you. And so if you look at it, we have in the dash boxes, there are two dash boxes, and I will start with the upper one that's labeled higher bandwidth part. Now, and what's shown here is simply just the signal path of the op-amp inside. Now, this high bandwidth part, or the block is also called main amplifier, this is your standard linear amplifier, so there's nothing special about it. And this path pretty much determines the gain bandwidth of the amplifier itself. Now, moving to the lower block that's in the dashed lines, you see a lot more things, sub-blocks going on. And one thing I want to point out right away is that you see all the signals are routed differentially, so that also helps in optimizing errors or minimizing errors like common mode errors or so forth. But let's go into the sub-blocks themselves. So the first one that's also tied to the inputs of the amplifier is called chop switch, and we see the same block occurring on the output of the auxiliary amplifier. So those are the set of switches that are driven by a multi-phase clock, and that facilitate commutating the inputs back and forth, and hence doing the correction. Now, as a very simple generic example is, for example, if the input of the amplifier is 4 volts, plus 4 volts. And in the next phase, we switch the polarity, so we have minus 4 volts. So if you average those two, you come out to 0. So that's in very simple terms how the amplifier operates. Now let's quickly switch back to the slide. And the auxiliary amplifier is simply a high gain, a slower amplifier that has a very high open loop gain that is needed to optimize for very low correction or very low offset at the output. So we're talking about correcting from about 10 millivolts on the inputs to down to into the microvolts when everything is done. The last block I wanted to mention is what's labeled synchronized switch cap filter. That is a needed filter to notch out harmonics of the clock frequency that's always in the output spectrum.
All right, thank you, Stefan. Appreciate that. So this unique architecture of self-correcting itself for offsets leads to a lot of benefits, but these benefits have been well documented over time, so I don't want to spend a whole lot of time on there, but I think it's important to just point that out once again. And a lot of times when we're talking about zero drift op amps, I find a lot of terms thrown out like ultra high precision or ultra performance, and the question always comes, well, what does that really mean? Can we monetize this, or not monetize this, but quantify this a bit? And so to do that, I put together a little comparison chart that compares a general purpose amplifier with one of our zero drift amplifiers. So if you look at the middle column there, we're showing the MCP6401, which is a general purpose amplifier relative to, say, our 6V61, which is shown in the far right column, which is implementing the zero drift architecture. As you can see, these are both relatively same speed, operating on the same operating voltage range. However, there are some vast differences in some of these other specifications. Initial offset is over 560 times better. We see drift over 130 times better. Other offset-related errors, such as common mode rejection, power supply rejection, all of those are also very, very much better relative to a general purpose amplifier. So this helps to put some numbers behind this performance. Now, when we talk about drift, I was showing a drift being 130 times better. It should be pointed out as well that that's comparing a typical number for the general purpose device versus a maximum number given for the zero drift, which that's pretty common that for, say, a non-zero drift device, they don't even specify a min and max.
That's correct. Yeah, it's important to really focus in on the zero drift, on the zero drift and the drift specification of zero drift amplifiers, because keep in mind that for a system, you are usually doing a system calibration to calibrate out the initial offset. So maybe a couple of millivolts of offset wouldn't be too bad. But once the system is calibrated and you really have your system subjected to, let's say, a wide temperature range, you are pretty much at the mercy of whatever amplifier you have, and as it drifts along with temperature. Now, that's really the point where zero drift amplifiers shine and really become important in their functionality. That, with a so much better, so much reduced drift, you can really calibrate your system and also have very stable, extremely stable behavior over temperature.
Right. Great, thank you, Stefan. All right, at this point, we're going to kick it back over to our booth and see what Mitch and Rachel are up to.
Hey, actually, we have a couple of questions. The first question goes back to chopper stabilized. When you say chopper stabilized, the audience wants to know, does that mean there's other types of zero drift? Could you just one more time review the types of other types of zero drifts?
Someone sent an email on this one, so thank you for your questions, everybody.
Yes, thank you for the question. So, Stefan, you touched on this before.
Yes, that's actually a very good question, because I mentioned auto zero, for example. That is an architecture that was used initially, and the main difference here is auto zero uses a sampled system where actually the input is sampled, and then the inputs for the correction pass are switched off of the inputs. Now, typically you will find, if you compare specifications, that the auto zero leads to a even lower initial offset, and maybe it's fair to say also a little bit higher on the drift. The important thing to mention here is the sampled behavior of the system of the auto zero amplifier, because now we have somewhat of an consideration of aliasing effects and so forth, and noise shaping is a little bit different there. Now, if you recall the slide that we showed for the chopper stabilized amplifier, the inputs are always connected, so there's no sampling going on, so there are no aliasing effects to be considered.
Okay. But regardless of the architecture, whether it's an auto zeroing, a chopper stabilized, or some hybrid combination of both techniques, the design considerations that we're talking about today still apply, right?
Absolutely, yes.
Okay, great. Thank you again for the question. That was good. When we're talking about the benefits of these zero drift amplifiers, I think it's also important to point out one of the demo boards that we have. This is actually an evaluation board featuring our MCP 6V01 zero drift operational amplifier. And what I really like about this board is that it allows the user to easily manipulate the environmental conditions and see how the amplifier actually responds to those changing conditions. So you can change the supply voltage, you can change the common mode input level, and see what happens if you step, say, the input common mode level. How does the amplifier respond to that? Of course, you can sample, or you can also vary, say, temperature across the board if you like, but this is a very easy board in order to really get the full experience of what these amplifiers can do and how they react to changing environmental conditions. Okay, on that note, I would like to go ahead and switch topics now to more of the system design considerations when working with these somewhat unique amplifiers. So the first topic that I'd like to bring up is leakage currents, or sometimes called bias currents. These are the currents that you see on the input pins of the amplifier, and how they vary from, say, a traditional amplifier.
Yes, so on this, if you're familiar with typically CMOS linear amplifiers, you know that those have very low leakage current in the pico amps or so. And when you talk about leakage current, it's what's labeled as a bias current, and also at the same time offset current. Typically on CMOS amplifiers, it's just the gate leakage current that appears as input bias current, and as you go up in temperature, leakage increase due to effect of the leaking of the ESD diodes.
That's Stefano, if I could just stop you right there.
Sure.
That's a great intro to that, and we'll talk about the definition of what bias current actually is too here in just a sec. But let's first quickly take it back to the booth to Mitch and Rachel.
Yeah, hi guys. We do have another question that came over YouTube. Does zero drift refer to zero offset drift as a function of temperature? That's the question from YouTube.
Thanks again for the question. Sorry, go ahead, Stefan.
Yes, absolutely. Yes, that's exactly what we are talking about, and I apologize if we didn't make it clear up front. So yes, we are talking about zero drift, or the drift of the offset voltage as it occurs if you have the amplifier subjected to a temperature range.
Suppliers are a little bit optimistic by saying zero drift. Obviously, it's not zero, but it is extremely low. In a lot of cases, low enough to where a system designer can just assume that it's zero, right?
Yes, absolutely. I think it's important to point out that the drift specifications are by now that low that even thermocouple effects on the PC board come into play. So sometimes, the drift of the amplifier itself gets buried by other effects. So that makes it almost zero.
And also, we're talking about zero drift, not only in terms of drift over temperature, but also drift over time, which could also be a factor.
Yes, that's a very good point also, that typically, amplifiers will exhibit an aging effect over time. It's very hard to quantify this, but by virtue of the self-correcting feature, zero drift amplifiers are much more stable in that regard.
Okay, great. All right, again, thank you for the question. So glad we got that covered. All right, so we were talking about input bias currents.
Yes.
So if maybe we can pull up a chart here that shows a little bit more about the definition of what these currents are.
Oh, yeah, okay. So this to very simply remind ourselves, if you look into a data sheet, you will find the term input bias current and input offset current. Now, on the input bias current, keep in mind that this is actually the average of the two bias currents that's generated flowing in both inputs, as you see here labeled IBN for the non-inverting input, IBI for the inverting input. So both are summed together and averaged out, and that becomes the input bias current spec in the data sheet. And the offset is simply the difference between the two input bias currents.
Right, thank you, Stefan.
Sure.
Yes, so given those definitions, let's apply some numbers now to those definitions and actually see how that would relate to a real amplifier.
Yeah, I think that helps. So here in this example, we picked the MCP6V06, and you won't find those exact numbers in the data sheet, again, because input bias current is the average, but the individual currents are noted here. So for example, on the non-inverting inputs is 37 picoamps, on the inverting inputs is plus 49. So if you average those out with the equation that I showed you before, you get an average of only 6 picoamps for the input bias current. But again, I mentioned that the offset current is a difference of the both. And in this example here for the zero drift amplifiers, so if you combine those, you end up with about 86 picoamps. So here you see that based on the nature of the two individual input bias currents, the input bias current is fairly small compared to regular amplifier, but the offset is rather large compared to a standard linear amplifier. Usually on a standard linear amplifier you would expect almost the other way around or so. So there's always an additional term that comes into play for zero drift amplifiers, and that's, if you recall the initial slide I showed you, the set of switches. Those are transmission gate switches, and there is a charge injection effect happening, and that creates an transient term which gets time averaged, but it becomes part of the input bias currents of the zero drift amplifier. So that's why you see typically zero drift amplifiers have a higher input bias current than linear amplifiers.
Okay. So possibly higher bias current, and then also certainly a higher offset current, which might come into play when you're figuring out, say, your air budget.
Yes. So that's certainly something to watch out for, especially in a system environment if you have to deal with high impedance sources.
Okay, great. All right. On that note, let's once again check in with our booth and Rachel and Mitch.
Hi. We have
Hey.
a question here.
Yeah, so the question coming in from YouTube is, although CMRR, PSRR, and offset are much better, power consumption seems higher. How does this compare to general purpose in battery applications?
That's a good question. Thank you.
Yes, that is a very good question.
Yes.
Stefan, do you want to address this?
Yeah, sure, certainly. Let me take this. It's a very good observation, excellent, because that was also something that it's not immediately clear. But so to the PSRR and CMRR rejection ratios. So again, the numbers that were shown here, those were DC rejection ratios, and of course, because of the differential path and the self-correcting features of the zero drift amplifiers, those effects get corrected at the same time as they occur. So there's added benefit of zero drift amplifier, because in effect the common mode rejection and power supply rejection refer to offset.
Right. They're
So
related to the offset.
Now, as with everything, there's a trade-off. And if you recall again, the initial slide that showed the architecture, we had all this additional circuitry down there at the bottom that, of course, has to be powered somehow. And so there is an oscillator, there's a clock circuitries there's an additional amplifier, and actually that amplifier block consists of a number of amplifiers. So those need to be biased correctly. And that means you have to spend a few more microamps on overall to achieve, say, for the same bandwidth class. So I think it's fair to say that you will always find zero drift amplifiers. They are, for their bandwidth, they need a few more, a little bit higher power. Now, if you are have to live with the power budget, you might be able to find a zero drift amplifier that fits your power budget. And if you're flexible on the bandwidth that you require in your system, then maybe you find one that rather fits the power budget than the bandwidth requirement.
Right, we do see some great applications for these zero drift amplifiers in battery powered applications with new process technologies, new and improved design considerations. These devices are becoming lower and lower in terms of their supply current. So they are still relevant for battery powered applications, but as Stefan mentioned, you need to be concerned about selecting the right amplifier that would fit your power budget and still satisfy your other performance needs.
Yep.
Okay, great. So talking about bias currents, let's switch gears a little bit again and talk about noise. You mentioned a little bit about the noise profile being one of the big benefits, if you will, of these zero drift amplifiers. So let's start with
Yes. So initially I mentioned, if you recall, that the self-correcting architectures, they also shape their noise. And
right.
it's very important because that becomes one of the key features of zero drift amplifier, especially as it applies to, let's say, sensor signal application where you have to deal with low level, low bandwidth type of signals. And to illustrate this a little bit better, we've prepared another slide to compare the traditional amplifier, the noise profile of a traditional amplifier, to the one of a zero drift. So let me start with a traditional amplifier here shown in the red curve. I'm sure many of you are familiar with this. You have essentially two portions. To the left, the slope portion is the 1/f noise. Now that's an intrinsic noise that based on process parameters and so forth. And then it flattens out and it becomes the flat band or wideband noise, going up to higher frequencies. So that's a very typical profile. Now, compared to this is a zero drift amplifier. Oh, you know what? Before I get to this, let me mention the 1/f noise rises at a rate of about 3 dB per octave, and especially if you are dealing with sensor signals in low frequency range, let's say starting at 0 up to 100 or 1,000 hertz or so. In this particular case, the 1/f noise would be right in the middle of it. So, and also, since this is your signal bandwidth of interest, you would have a hard time, or it's virtually impossible to filter it out.
Right.
So you're stuck with it.
Okay.
That's sort of bad news because if we go through an example and we estimate, well, our signal is in a bandwidth of 0.1 or to 100 hertz, then the 1/f noise on a traditional amplifier in this particular example here would account to about 80% of the total noise, which could be, ruling out this type of amplifier. Now,
and like you said, you can't filter it out, but you also can't average it out either, right?
No, absolutely not.
So,
no.
so you would, like you said, you're stuck with
you
it.
would affect your signal just as much.
Right.
So.
Right. Okay.
Now, if we have if you switch briefly back to, thank you, the blue curve here is showing for the zero drift amplifier. Now, it's immediately visible that it starts out flat and remains flat for quite a while, and then transitions into a hump and a peak. So again, that is the noise shaping effect that happens in the zero drift amplifier. So a first order also 1/f noise is considered a slow moving signal. And since we are correcting at a rate of, let's say, every 100 microsecond or so, which is fairly quick, 1/f noise falls into that region of correction, and that's why 1/f noise can be very beautifully corrected for. And then you remain, you have the noise as a flatband noise in that region. Now, the downside is, as mentioned, as part of the noise shaping effect, we have the hump that has moved to the right here, to the higher frequencies. Now, there is a couple of things going on. Now, if you recall, on the architecture, we have the main amplifier and we have the correction path amplifier. Now, at one point at the end, those two signal paths have to be merged back together, and they have to be compensated internally, individually, to assure stability. And that causes, this hump effect there, what you see, that's around roughly 20 kilohertz or so in this particular case. and that causes the noise to rise up. And it's sort of inherent in pretty much all of the zero drift architectures. And the spike I wanted to mention is simply the feed-through of the clock tone.
Oh, okay. Because of the internal switching that's going on.
Yes, the oscillator, internally oscillator, and the switching action that occurs, yes.
But manufacturers, including Microchip, there's actually a filter to help make that switching noise as minimal as possible. No?
Yes. Now, keep in mind that the spectrum that we showed here was already after the amplifier, so that includes the reduction of the internal notch filter. Otherwise, it would be higher. But also keep in mind, again, you would want to have use those zero drift amplifiers for sensor signal applications. Mm-hmm. And again, they're limited to, let's say, a kilohertz or so, and also at the same time you want higher gain. So the bandwidth of the amplifier will roll off anyway at the higher frequencies, and it's always suggested to have a passive, even a simple RC filter to roll off those noise humps and the tone.
Okay. So they're high enough in terms of frequency that makes it relatively easy to filter out those.
Yes, yes. Mm-hmm.
Okay, great. All right, let's see what the booth is up to, and again we'll cut back to Rachel and Mitch.
Hey guys, so we were getting some questions here in the booth, actually, in addition to the live stream, in regards to that noise graph. So the question was, we noticed that for the non-zero drift amplifier, the noise will be lower. Is that always true?
That's a very good question.
Okay, so if we could go back to the chart, I believe what they're talking about is for the traditional op-amp that we're showing here. They're talking about the flat band or the white noise region, where the 1/F noise is no longer the dominant noise source, so higher up in frequency. And as you can see, just on this particular graph, the traditional op-amp is shown as being slightly lower than the zero drift. The question is that always the case?
No, that's a very good observation, as it so happens in this particular case, because remember, there are actually amplifiers behind those noise curves, and we just picked one that show visibly bringing home the effects here. But no, you'll be able to find zero drift amplifiers that have a noise floor that's lower, for example, than traditional ones. Mm-hmm. So you should be able to find those. Now, keep in mind, noise usually comes at or lower noise comes at the expense of a higher current, meaning supply current, right. So which means if you're opting for a lower noise amplifier, you probably find that those amplifiers require a higher power to begin with. But that's true for any amplifier, whether it be linear or zero drift.
Right. Okay. Thank you, Stefan. Yeah, I believe that regarding that chart, the goal there was to show the two different profiles, if you will, between the traditional versus the zero drift amplifier, not so much the absolute levels. Right. Mm-hmm. So, but thank you for the question. That was a good clarification. Continuing on with the discussion of noise, I'd like to talk about EMI, or mechanical interference. So one of the let's just talk about that first. I have a board I want to show you all as well, but we'll get to that in just a second. Sorry, I'm getting ahead of myself here. So, Stefan, EMI, it seems to be that's becoming a bigger and bigger issue in this world. Can you talk a little bit about that?
Oh yeah, absolutely. Electromagnetic interference, or RF interference, as it typically happens because we have so many noise sources, RF sources around us, cell phones, Wi-Fi repeaters, access points, and so forth. So they're all operating at hundreds of megahertz, and it has become quite a subject, especially if you have amplifiers that resolve down to microvolt levels, and you can pick up minute changes there. Now the interesting part here is that somebody is working with a 1 megahertz op amp, and the question arises then, well, I only have a 1 megahertz op amp. Why would I need to concern myself with 4, 900, or even 1.8 gigahertz? So, and on the surface, that's a valid question. It's not intuitive why it would matter, but consider that pretty much every amplifier has ESD diodes for protection inside. and those diodes can pick up RF and act as rectification devices. And what results is simply an additional offset term that may be even unstable or occurring once in a while. So regardless of the speed of the amplifier, it's more critical for low bandwidth amplifier because, like I said, the sensor signals are low level signals that need to be resolved. So small changes can play a big role here.
Right.
So, and also in to extend on this a little bit further, we've prepared a slide here to kind of visually again show the effects of EMI as it occurs on the various conditions. If you, okay. So it's a bit of a busy slide, but I'll walk you through it. Now I'm starting on the upper left-hand corner, which labels standard amplifier without external filtering. Now what we have here, the orange trace, this is our RF signal. Now it's pulsed in order to make it more visible, the effects of it, and it's simply riding on a noise. But it's about if I recall correctly, an 800 megahertz pulsed RF. And what we have here, this RF signal was subjected or put to the inputs of a regular amplifier, a CMOS amplifier, I should add, and the output of the amplifier is shown on the lower purple curve here, and you see very clearly every time an RF pulse occurs, we have a jump in the output signal. It's quite the scale here is half a volt per division, so it jumps quite a bit, roughly half a volt every time an RF pulse occurs. So you see that.
So it shows up as this offset shift when that.
Yes,
Okay.
and then the important thing to remember here, it's like this could be varying because RF is not really constant, and all of a sudden you have an offset component that varies, and you don't know where it's coming from. But it could be EMI related. So let me go to the next example on that slide. The standard amplifier, and where we added some external filtering, so just a simple RC on the inputs to try to catch the RF before it hits the amplifier. But there's still an amount coming through, and you see the output signal, the purple curve, is still disrupted by those RF pulses. Now, okay. Can we stay on that slide real quick? Sorry about that. Because I wanted to now mention also the last example that we have here. It's labeled EMI amplifier. That means we have an amplifier here that has internal EMI filter built in, and so there's no external filtering going on right now. And we see very clearly that the output remains undisturbed, so the RF is clearly filtered out and does not cause any trouble in this case.
So having the filter on chip is even better than just having a filter, say, external to the chip.
Yes, and it's we are talking about simple RC filter, but you could clearly see the superior effects by having the RC filter inside the amplifier, and not having extra traces that can pick up additional RF and so forth. And also I should mention that in the case of Microchip's EMI filtering, we are using a dual pole filter. So we are going a little step further to have a better roll-off and have a better attenuation as it occurs inside.
Right, great. Thank you, Stefan. All right, let's cut over to Mitch and Rachel and see what they have.
Hi, yes, we have a question. It's a big question. We had to write it down because it's a long one, but let me try my best. Here we go. It is, what if I need to use impedance driver amp after a high impedance sensor, and then the zero drift amp, but that is driving and not the zero drift? Or, but that preamp stage is driving not the zero drift. There you go, my bad. I'm so sorry. Do you understand? Do you want me to read it again? Yeah?
Maybe one more time, please.
Okay. I can read it again. Okay, so it says, if I need to use impedance drive amp after a high impedance sensor, and then the zero drift amp, but that preamp stage is driving and not the zero drift.
Okay, let me try to take a shot at it. Now, first of all, high impedance sensor, I mean, the term is somewhat relative. It's hard to make a clean cut. You know, it could be 100 kilohertz. It could be a pH probe, which is very high impedance. So if it's a pH probe, we're talking about mega or gigahertz, ohms or so, then maybe a zero drift amplifier, based on the input bias aspects we talked about earlier, maybe a little bit of a problem. Now, scaling down into the tens of kilohertz, a zero drift amplifier may still work fairly well there. Keep in mind, as far as the input impedance goes, it's pretty similar to a regular linear CMOS amplifier. So it doesn't, zero drift amplifier is not in its input impedance down into the hundreds of kilohertz or so, where it becomes a problem. It's still, in the gigahertz range overall. So, but if I understood the question correctly, that it sounded like somebody wanted to maintain or keep a linear amplifier right after the high impedance sensor, and then a second stage facilitated by a zero drift amplifier, and that's perfectly fine. I mean, you could preserve your maybe initial low noise, low drift signal with a second gain stage. You can also develop the second gain stage as an active filter or something, and use a zero drift amplifier.
And still get all the benefits of the zero
Absolutely,
drift.
yes.
Right. Okay. Rachel and Mitch, does that answer the question you feel?
So yes.
Okay, good.
Yeah. Actually, we have another one. This one's much easier, though.
Yes.
Okay, I'll field this one then.
Okay. So the question is, can a zero drift amplifier replace an INA?
Well, that is a very good question. So, yes and no. So obviously with instrumentation amplifiers, and even instrumentation amplifiers today, including those from Microchip, implement a zero drift architecture. So we already have monolithic instrumentation amplifiers that also utilize this zero drift architecture internal. However, you can always roll your own, if you will, instrumentation amplifier by using discrete operational amplifiers. You can do that using general purpose amps or precision amplifiers, even zero drift operational amplifiers. So you can certainly do your own instrumentation amplifier design using these zero drift amplifiers. In fact, Microchip has a board that highlights these two different solutions using an instrumentation amplifier, monolithic instrumentation amplifier, as well as a 3 op amp instrumentation amplifier that utilizes one of our zero drift amplifiers. So you can check out our website on that. That's the 6N11 Wheatstone Bridge reference design that I'm referring to, which we'll put that in the reference material section on the live stream page following this broadcast. Stefan, anything to add to that?
No, fundamentally, you can configure zero drift amplifiers, and it's very similar or similar as you would linear amplifiers. So fundamentally, there's nothing that would prevent you. Again, you wanna look for preserving what you're buying in the first place. You know, you're buying all this precision, and you want to make sure that you preserve it. You know, putting components around it. For example, opting for very high values of resistors is probably not a good choice, because the resistors add noise. They would have a drift component to it, and so forth. So you want to be mindful about, not destroying what you paid for in the first place.
Right. Good point. Okay. So as we've been talking about EMI and the effects that has on amplifier circuits, I want to point out a board that we have, but this is based on our MCP 6421, which is actually a general purpose amplifier, but it has the integrated on-chip EMI filtering. And that's important to note that as we're talking about EMI, yes, I know this whole live stream was regarding zero drift amplifiers, but the effects of EMI affect all electronics, all amplifiers included, whether it's general purpose or zero drift. But so this is a general purpose device, but again, the effects of EMI are essentially the same for all amplifiers. What I like about this board is it allows the user to input their own RF signal, so they can put in a signal that's of the magnitude and of the frequency that they desire, and you can see how the amplifier goes about rejecting that interference. Okay.
Maybe one additional point
Yes,
in the realm of the EMI, that we pretty much on all of our zero drift amplifiers have specifications in the data sheet for EMI rejection ratios. So it's also important to point out, because sometimes we get the question, well, are there industry standards and so forth, but we show our specifications under which conditions in terms of amplitude and frequency they were taken and so forth. So if somebody wanted to retake a measurement or so, that's certainly possible, and redo the curves. And we also have typical performance curves that show EMI rejection ratio over a whole range of frequencies. So that should help designers to get a bit of a feeling for what the rejection ratios of the amplifier themselves does, and give them a bit of a margin for when dealing with EMI issues on the system level.
Right. Okay, thank you, Stefan. And let's take it back to the booth one more time to Rachel and Mitch, please.
Yeah, this is a good time to talk about some of the nomenclature associated with EMI, and we get common questions on this one. Even in the booth here, we're kind of curious, what's the difference between some of the nomenclatures we hear? EMI hardened, EMI enhanced protection. Could you guys just briefly go over what the difference is, or if there's a difference?
Good question.
Yeah, I think in general they all refer to the same scenario of what we saw on the slide with the RF pulse, that an RF interferer is an environmental condition that the circuit or the system, like a board, has to work in, and everybody's trying to describe what the behavior is under those conditions, just like a temperature effect of the amplifier. So again, when we say the EMI rejection is 80 dBs at 900 megahertz, at a certain level, and that is something that a customer so could take the board and replicate for. But in terms of like EMI hardened, EMI improved, and so forth, I think everybody's talking about the same effects that RF pulses, like mentioned earlier, from cell phones or any effects could even be high spurs from motor control engines or so forth that migrates around. So it's all a matter of hardening or reducing the effects of such EMI, electromagnetic interference, on the amplifier, and making the signal chain more robust.
Okay, so regardless of what name they give it, it sounds like the real, where the rubber hits the road, so to speak, is where the specifications come into play. Under what conditions are these being tested, and what rejection do they see under those given conditions?
Yes.
And that will allow a user to be able to identify and compare various amplifiers in that regard, regardless of what they call it.
Yeah, typically you will find, if you're picking up data sheets or so, that EMI rejection is typically put on the front page these days. So if if a data sheet doesn't have that mentioned on the front page, and it's fair to say that most likely it doesn't have internal rejection filters or any other means of EMI rejection.
So the final topic, Stefan, that I wanted to bring up, again talking about design considerations for working with these zero drift amplifiers, is time domain considerations.
Yes, actually, and that's a good point, because we're getting into an area where we talk about trade-offs again. Time domain behavior, especially large signal steps and so forth, is a bit of a challenge for zero drift amplifiers. And the reason for this is simply, if you recall, we have the main amplifier and we have the whole circuitry that does a correction path. Now, the correction path is a non-continuous correction, like I mentioned earlier, corrects maybe every 25 or every 100 microseconds. So if you envision you have the amplifier is in a closed loop condition, it's stable, and all of a sudden the input signal jumps. So the both inputs of the amplifier are getting pulled apart, which is a huge delta between the inputs. Now that could be as bad as the amplifier going in temporary open loop conditions. Now the internal workings, and especially the correction loop, has to catch up with that jump in order to bring it down to 0, correct the offset, settle and correct the offset, and so forth. So, and because of the non-continuous works of the correction loop, that only can happen so fast. And that's usually in how fast the clock runs. So which means you will see on the output almost like a mini step response before it settles, and then settles into the final low offset value. So what you'll find on zero drift amplifiers is that they also have much longer overload recovery times, or respond quite a bit slower to transients than compared to linear amplifiers. Mm-hmm. So that's something that you want to be aware of as a system designer. If there's an error condition that occurred that disrupts your signal, and all of a sudden you have to wait tens of microseconds or so until you have a valid signal again.
Waiting for the slower correction loop to catch
mm-hmm.
up, if you will.
Right. to correct and settle and
settle to the final offset value. Okay, well that was the final topic that I wanted to cover today regarding design considerations for zero drift amplifiers. So one final time, I'd like to put it back to the booth and see if there's any wrap up from Mitch and Rachel.
Yeah, thanks. We did have a wrap-up question that came in over the live stream, and that is, what is meant by rail-to-rail op amps?
Okay, so the question is regarding rail-to-rail op amps. You want to address this? Yeah, let me start. Now, rail-to-rail is a common term. It's been around for a long time. Now, we have to distinguish. Does it mean rail-to-rail inputs, rail-to-rail outputs, or rail-to-rail inputs and outputs? So you will find, amplifiers in each of those three categories. Now, rail-to-rail inputs is usually you will find that the amplifier is capable of acquiring correctly the input signal that even goes beyond the rails. Typically, it's a couple hundred.
And we're talking supply voltage rails.
Supply voltage rails, yes.
Right. Okay.
So. If you talk about rail-to-rail inputs, then the amplifier might be able to, go 300 millivolts above the rails there, and still acquire a valid signal. Now, on the output is a little bit of a different scenario. Rail-to-rail output, in really strict terms, you will never have rail-to-rail outputs, because there's always some headroom that is left. Otherwise the output stage wouldn't function correctly, mm-hmm. and you're running out of loop gain anyway. So there's always this range, and it's specified in the data sheet on low power, like say CMOS op amps. It could be as little as 5 millivolt on each side that you can swing close to the rails, which means if you're putting in 0 volts on the inputs, and you're expecting the output to be at a certain range, you always have, towards the end of it, that few millivolts to contend with.
Right. So it's close to rail-to-rail.
It's close, yeah. It's
okay.
But it's also a function of the output current and the output loading, which means the more loading you put on, the more headroom the amplifier will need. So that's something the system
design. So it is a function of the load as well.
Yes.
Okay, that's good to know. Okay, Rachel and Mitch, anything else from the booth?
That's about it, but we did have one last question from Isaac about is there a nice collection of design notes that can be referred to that we could find?
Actually, I made a note for myself in case this comes up. When I talked about the EMI rejection graph and that one busy slide there, we have an application note on this. It's the AN1767. So that has a lot more explanation of what was done there, what the configuration was, and so forth. And that, of course, can be readily downloaded from Microchip's website. We also have a couple of there's a user guide that comes with those demo boards, of course, as Kevin mentioned earlier. There's reference material there. And
we also have a few app notes, I believe, that talk about AC versus DC error sources with amplifiers. And again, that's not just zero drift amplifiers, but amplifiers in general.
Yes.
Those might be quite useful as well. I made a note. I will go ahead and post those resources on the Livestream webpage as well. So that would be another easier place to perhaps find all those resources. So Rachel and Mitch, anything else?
I think that's about it. Those are all the questions that we've got. It's been great. Thank you for all of your comments and questions, and thank you for answering in the live stream if you can. That's been wonderful as well.
Yeah, I just want to remind everybody that we can take your questions if there's additional questions at Livestream at microchip.com.
Yep,
So if you have any trailing questions, that's where you can send them over to us, and we'll pick them up and answer them back to you.
Right, exactly. And also, if you don't mind, if you are new or you're seasoned in this with Microchip, if you don't mind subscribing and hitting that like button, 'cause that helps us what we can do for you and stuff like that. So those are some homework assignments for y'all, okay? All right. Thank you so much. Back to you, Kevin.
Okay, Rachel.
All right, Mitch and Rachel, thank you both for your time today. I appreciate your help. And Stefan, it's been a pleasure. Thank you for joining
Yeah,
us.
thanks for having me over.
So from all of us at Microchip, thank you for joining us, and we'll see you next time.
Goodbye.